Okay, so first thing I'd like to talk about is the following. In our list of things that were due, we had project number 2, part number 2 that was going to be due next week, but I changed the due date because I haven't talked about it yet. Project part number 2 is where you create essentially a miniature lit review, like an introduction section, and a methods section where you describe what your research questions are and how you are going to test them with models that we use in class. Right? So that's what project number 2 is, essentially. You can look at the details of the document of the project assignment if you want, but that's it in a nutshell. What are you doing? What are you testing? How are you going about analyzing? For those of you who have empirical data, that's pretty straightforward. Those of you who have empirical data, I would say that's straightforward. If it's not straightforward, think clearly about what your research hypotheses are. Those have to be paramount to what you do. We don't do statistics in the absence of a hypothesis, or at least we should. I guess we could do statistics for the fun of it. I do, but you don't usually get your papers published that way. So you have data, you have hypotheses that you had a priori to collecting said data, and now you would like to go and test them somehow. So that would set up a series of types of models, and then better yet, to be really clear, what models go into which hypotheses, and specifically, what do you learn from the models to be able to give you information? Do you reject the hypotheses, you change them, and so forth? So essentially, that's what the project part 2 is. I like part 2 because then I can help you set up that a little bit more formally, so that project part 3, which is really do it, is a little bit more straightforward. If you have, so I'm putting the due date for that now on February, April 1st. April Fool's Day. All right?
So this is legit, right?
This is legit.
You sure?
Absolutely. Absolutely. Project part 2 is due on April 1st. For those of you doing a simulation study, it may be a little bit different. What I'd like to know about the simulation study is more, what are your research hypotheses? And what are you doing in terms of what's the simulation? How are you doing your simulation? What are the specs? And I think that's basically it. How does that tie into your hypotheses? And if you have a chance, again, in terms of literature review, this is not like a master's or a dissertation where you're going to have to spend 8 years doing literature review. Honestly, I'm not in your field. I won't even be able to tell you. I can tell you for the simulation study, if you're doing one of those, I could probably tell you what's up with that. But I want you to at least give me a few background references to tell me what you're doing in your study, but not a lot. It's mainly here, it's research hypotheses leading into statistical tests, leading into answers. And same thing for the simulation study, research hypotheses. A little bit of lit review. What's been done? A little bit. I don't know what a little bit means. I don't want to put a page limit on it. But just, some references tied together with some text. Okay? Sound good? I figure it gets so serious now. Evidently, some of you are unhappy with me. Is this how it works?
Don't look at me. I'm doing it late.
What's that?
She's looking at me like I did it, but clearly.
How many of you are unhappy with me? Not with me. That's good. Anyway, so that's project 2. Questions on project 2? Anything you want to know? Want to think about? It's a chance for me to give you feedback on the actual analysis. That's how I look at it, right? Project part 1 was, let me help you form some hypotheses or think about what you're doing and see if it applies to class, and also think about your data. Project part 2 is, cool, you thought about your data. I'm cool with the bigger topic. Now be specific as to what you want to do, and I'll help you set it up. And then part 3 is do it. Another nice thing about it coming on September, I can't even get the months right. Whatever the 4th month of this year happens to be, is that it allows us to get a little bit more into factor analysis. So you can write, a lot of you are doing studies with factors in them. So you can write more about that, talk more about code if you'd like for it. Wow. So anybody? I'm going to take a drink. Pause here. Okay, moving on. What did I say last week? Insurance is open. Insurance is closed. Questions are closed. Okay. Next step. I have a list. What my plan for today is, I'd like to go back, and I'm gonna actually, in the context of R and in the context of coming up with just theory, we're gonna start with like a 3-variable path analysis. I'm gonna walk us through beginning to end, because there's some things I wanted to note that I saw in homework this week that I'd like to talk about that I didn't either discuss in class or didn't discuss well enough. And I think in that context, it will open up questions about this homework that you just turned in. But we certainly will hit that up before the end of class. So I think I'm going to have you hold your homework questions for an hour or two. Frowning? Uh-oh, no? Do you really want them out, or is it just hour or two? No? Sorry. My apologies. Yeah, sorry. Hold off on the homework questions. I'm sorry, Kim. I didn't mean to pick on you. It's so there's such a small room. I can see all of your facial expressions. So I know when you're on Facebook, it's okay, and I know when you're really unhappy with me, Devane. But no, that's why I'm concerned about you. So when you frown, I want to know. But I apologize for picking on you. Hold off on the homework questions for right now, but I'm hoping that this example will pick up some of them as we go. And other things that you may have had questions about as we had gone along, such as questions regarding the analysis methods. What in Levon, what a tilde is versus what a double tilde is versus everything else. And again, I apologize right now. I'm looking at my phone. My phone starts flashing, and I start getting worried. I'm still on call. There's still no child yet. He's evidently is alive, but isn't officially alive yet. You know, so
He hasn't been left behind.
he hasn't been left behind. No. My wife is wanting him to be born. Any way, which way is possible now. She's tired of being pregnant. I understand that's what you go through. I sort of think that's probably nature's way of getting you ready for the whole labor and delivery business. Boy, what a mess. So I'm a little distracted as I talk. If I see my phone flash, I will check it. Can I give you a story? I like these stories. In grad school, I had a professor. I'm going to be that professor now. I never thought I'd be this guy, but I'm going to be him. I went to grad school right when cell phones were starting to become, everybody had them. We were in that transition phase between a pager and a cell phone. Anyone have pagers before? I used to roll around with a pager. That was awesome. Yeah, I thought I was really cool. Anyway, so I'm in grad school, and a phone rings in the class. And the professor's like, oh, I got to take this. And so he takes it. I mean, that's what happens. I guess we have emergencies. Okay, so he takes it in front of this class. He's teaching the class. He's teaching, like, I don't remember which class it was, Multivariate or something. He answers the phone. He's like, hey, whatever. And he's like, oh, yeah. And so he starts to proceed to talk to who turns out to be his son. His son wants to order pizza. And so he's going to order pizza for his son. So I promise you, I hope there's a good legitimate reason for the phone going off. But if for instance, I saw my phone flashing and it was a text. My sister just texted saying my mom dropped her phone in the washing machine and it's broken, so I'm supposed to text her if any news comes. So everybody is waiting for this. But I will try to keep pizza ordering to a minimum. Okay? Oh, that's right. Oh, sorry. I've been trying to get a hold of you the whole time. So, I guess, so I'm going to start with R, but I guess I feel a little upset, a little worried. Devane, are you really upset? No. Okay. This is your doing, I take it?
I mean, we had this email conversation. You were told to be prepared.
Okay, this is what I was prepared for. I'm cool. He told me, I hope you're in a good mood. I'm in a good mood.
If you were in a bad mood, none of this would have happened.
No, I'm good. I try not to take myself too serious. I appreciate you asking. I try not to take myself too serious. For those of you who struggle with homework, I understand. It's tough, but I hope the struggle was worth it. It will be worth it, and I hope today will help put it into better context. So this is a good place for this review. So, remember path analysis? It's a terrible word. What is a good definition of path analysis? If someone were to say to you, hey, you're in SEM class, what are you doing? You're like, oh, I'm doing path analysis. The follow-up would be, what's path analysis? What would you tell them? Pain in the ass analysis. What's it? Did I hear? Did you answer? No. Okay, sorry. I'm over here trying to like get people to talk. Anybody? Path analysis is. I think we had a quiz question on this. Simultaneous regression. Very good. All right. So regression, linear regression, all that you've done before is a path analysis. It just has one endogenous variable. Right? Linear regression that you've done before is a path analysis with a saturated covariance matrix. Right? You're estimating the one residual variance there happens to be. So model fit in a linear regression, we don't even talk about it anymore because it's perfect. But a path analysis is a series of linear regressions where some of the variables, some of the endogenous y variables, are predicting other endogenous variables, right? So you've got things that are not predicting, those are exogenous things. They're predicting some variables in the model, y endogenous variables. And then some endogenous variables are predicting other endogenous variables. So excuse my analysis there. This is an analysis I'm doing for the dynamic learning maps, yada, yada, yada. Fun, right? Megan can tell you more about this. Do you enjoy databases, Megan?
No.
Does anyone else in here work with the CETE databases at all? Be glad. Okay, so today's example and today's material that I'm going to do, I'm going to use the laptop for everything. I'm going to do an example in R. I'm also going to handwrite on OneNote if I can get it to work. There it goes. Right here. So I am going to switch this over to teaching. And, wow, this is all my to-do list for this class. How about I just create a new page. And this will be SEM. Whoa, okay, got it. Why is it? Okay, select a region. Okay, thank you. I just want to type. I have somehow locked my function keys. I don't know why. Sorry. Anyway, I'm going to make this as my note documents here, so we'll call this SEM. This is lecture 7. And I am tired of OneDrive already. Boy. Okay, so here we go. The example that I'd like to start off with is one where we have a path analysis where we have 3 variables. And to try to make it so this transcends all data, I'm just going to call the variables like x, y, and z. Okay? So we're going to have a variable x right here. We're going to have a variable z. This is a path diagram of it. And we're going to have another variable y. And we're going to say that x predicts z, x predicts y, and y predicts z. So that is a path diagram, right? How many endogenous variables do we have? We have 2 endogenous. Endogenous. There, it's y and z, right? Those are the you tell that they're endogenous by looking at where. I can't believe this. This is driving me nuts. You're looking at where the variables happen to, which variables have arrows that terminate with them, right? That says that's being predicted by. Okay. How many exogenous variables do we have then? 1 exogenous. Right? And that is variable x. So So, what I'd like to do is describe this path analysis with a series of equations. And so we can jot down each of the terms that happen to be in the analysis itself, just to get more familiarity with what all the terms happen to be, okay? So I usually start with equations for it. Boy, I am about to lose my mind with my pen not working or my keyboard not working or whatever else. I have little patience for technology at the moment. So right here. So we have two equations. Since we have two endogenous variables, those two equations are for the variables, right? We have y and we have z. So what is the regression equation for y? Y equals, well, there's beta 0,
Just kidding.
and I put a y at the top saying that's the intercept for this equation predicting y.
Plus beta 1.
Beta 1 x, and that's predicting y2. So in my little notation that I do usually, I call that beta x predicting y. I do that again because we have so many slopes, we have so many terms. So this is saying this is the beta weight that multiplies x that's predicting y. Everybody good with that? What else do I need up here? Plus, that's good.
E or sinus.
E. Okay, so in a regression line, that's a good point to bring up, Devane. One of the bigger misconceptions that a lot of people have, particularly quantitative people, is that what goes on the line here, when you want to put error in, it's E. And it's E because this line is talking about what is essentially what goes with the data. This first part is your predicted value, right? This would be y hat, sometimes we call hat, right? This is what we predict a person's y to be given their x. What this other term happens to be is the difference between that prediction and the data. So on a regression line itself, E has to be itself. It's just E. It's all by itself. It's how far off we are from y hat to y. It's just that distance. So in my path analysis notation, I say this is E for y right here. Now, sigma squared E that you talked about, we're going to come to in just a moment. But every time there's a regression line, it's always E. Right? Okay? E, by the way, is something we don't observe directly. Right? It's only observed after we've plugged in x and we know beta 0 and beta 1 or whatever else. Right? So it's something that we have to go and start making assumptions about. That's kind of this will carry forward when we get to factor analysis. And you saw last week, the factor would show up on a regression line, but we don't observe it directly. So sure enough, we had assumptions about the factor. It had some type of mean, it had some type of variance. Same thing with E here too. All right, so what is the regression line for Z then? Z equals very good. Beta 0Z, that's the intercept for Z. Here plus, yeah. I feel like we're on The Price is Right, right? What's that game where they start revealing certain numbers? You know what I'm talking about? No. It would be, what's that? What's that game?
Deal or no deal?
Deal or no deal? Not quite. Although that would be I guess this is sort of like Deal or No Deal. Beta, you said beta 1 y, so we're predicting Z with y. This would be like the beta for y predicting Z, so it's like beta 1 if you want to call it that. All right, so that beta represents this slope right here. What else do we need to put there? We need to represent this slope right here. So what is that going to be? I heard x. There's a beta with it. Beta x predicting Z. Right? And you'll note this is why I am trying to differentiate all these subscripts and superscripts. X, our exogenous variable, shows up on the line for z and the line for y. So each beta in front of it has to be different. If I just called, for instance, this one beta 1, and I call this one beta 1, if you look at that from a mathematical point of view, what you're saying is the slope for these two are equal. Right? That's the same symbol there, so the same thing that goes into that symbol is equal in both. We can't do that, so we have to, I mean, that's a testable hypothesis. You can think about how to do that with constraints in Lavon, but we don't do that off the bat, right? We don't ever actually think that. So beta, this is beta y, for beta x predicting y, and this is beta x predicting z. Okay. And so then finally we have the error term, which is the error for z itself. And that's again denoting this error and that error are different values, right? For each person, we observe an x, we observe a y. We can come up with the predicted value for y with x. We can come up with the predicted value for z with x and y. But we're going to likely be off a little bit for z, and we're going to be off a little bit for y. So this is the residual or error term for each of those dependent variables. So in a path analysis, every dependent variable, every endogenous variable, has an error term with it. Right? Every endogenous variable, if you look at the path diagram itself, every endogenous variable that you can look at based on where the arrows end has a regression line. And so in the homework this week, whoa, I didn't want to erase that. In the homework this week, you had looked at, I liked this, I tried to make an assignment. I like it in some respects, some of it is a little bit difficult. But I liked it because it takes an actual empirical article from just a couple of years ago where they did a path analysis. In fact, they did two. And it tries to get you to replicate their analysis. But to do so, you have to decipher what their analysis is, and that's where coming in with this picture shows up. So the first step in doing that was to say, hey, how many dependent variables or how many endogenous variables are there for each of these diagrams? Once you figure that out, then you can figure out how many regression lines there are. And the regression lines show up for each endogenous variable. The step that goes with that, in Lavon, each of these regression lines is symbolized by the single tilde. Right? So Lavon is trying to get you to do regression where you replace the dependent or the equal sign with a tilde, a single tilde itself. That's essentially how I read it when I see the syntax. Oh, this is a nice linear regression line. On the left-hand side is my dependent or endogenous variable. On the right-hand side is what is predicting it. And then essentially implied in there are slopes for each of these terms. There's nothing in Lavon where I can specify E itself, so it doesn't show up on the line. And there is a line in Lavon that I guess we could have done where we put a tilde or put a 1 in front. The intercept is represented by the number 1. So how are we doing with all this so far? So far, so good? Okay. Where am I going, I guess is the question. Everybody's looking at me like, we got this. You got this, yes.
So beta x to z, that's basically the same thing as saying I equals 1 with an n on top, so we're going to start from the ending term. Is that what beta x, y basically?
No, what this right here, this beta right here you're talking about?
Yes.
This is talking about, literally, this is the regression beta weight that multiplies the variable x that predicts variable z. Right? So this is the slope for x predicting z.
Okay.
Right? So what is this? This is the slope for x predicting y. And because in the path analysis, variables, because this is a Megan, you said the word simultaneous regression, because variables can predict other variables, we can have multiple slopes for x. And that's why we have to have more terms to it, symbolically. Does that work?
Yes.
Awesome. Yes, Dan.
Can we put the
This right here, can we put it right there? Yeah. We could. I mean, if we could do algebra. If we wanted to do algebra with that, we could. For instance, we could take really what z is beta 0 z plus beta for y predicting z times the regression line for y, which is beta 0 y plus beta x predicting y of x plus error for that. And then we can plug in beta x predicting z and error for z, right? We could do all that if we wanted to. We don't in this case usually because we can get by without having to do that, given the algebra that we're about to actually go through and do a little bit. But you can conceptualize it that way, which is really in a path analysis what you're saying is if you've got a function for y and then you go and take y and predict z with it, simultaneously that's what's giving you what happens. But I'm going to go a step further though, Dan, and multiply this through, and I want to show what this happens to be here then, okay? If we multiply this part through, we get, let me give you the whole line, beta 0z plus beta of y, predicting y of z, times beta 0 for y, plus beta y of z times beta x of y times x. And this is weird, beta y of z predicting times error of y plus beta x predicting z plus error for z. Okay, so you get all these terms. Why I did that is if you were to go and kind of do the logic for all of this, I don't want to say this. This term and this term will end up being, well, here, let me back up. This term right here, you have the product, you have the slope of y predicting z times the slope of x predicting y. What is that thing in our path analysis? It actually has a very specific definition. Very good. That is this times that. That is the indirect effect. Right? So that's where we actually get some of our direct and indirect effects about. And so if you were to go through that process of multiplication, you'd see this. Where it starts to break down is we have error times a slope, and we get a little fuzzy when it comes to the actual logic here because error doesn't exist. But that is something that you can do. You can put that in. Did you have another thought on that? No. Okay. So yeah, that's actually that type of process of logic and algebra is how we get a lot of our results from path analysis when we do things. So you will see that in some technical journals when we try to work through certain results in path analysis. But it isn't relevant for our example at the moment, though. It's good to talk about. So what I'd like to do, there's one other part to this. So I struggle with the definition of what a model happens to be, right? A model happens to be several things. There's a set of variables and a set of equations and a set of distributions, right? So in this, one thing we're lacking is Devane had mentioned sigma squared when we talked about the first line. We have the following assumption about EY. What do we assume about the error terms for y, that first regression line? They follow a normal distribution. What's the mean of that? 0. Error always follows a mean 0, has a mean 0. Conceptually, why that's the case, if error's mean was more than 0, our effects themselves would be off systematically, which seems to make sense. It's almost like we have a bias to our analysis, and we don't want to have that built in. So error's means are always 0. What's the variance of error for y? Sigma squared. And I usually denote this error, and I put a colon and I put what error that happens to be for, right? Sigma squared error for the prediction of y. Now, conceptually, what is that term? What is the error for y in a regression line? Or what is the error variance? It's residual variance, yes, so that's variance left over. But what is it describing variability of?
The difference between the observed covariance and the
No, and that's not and that's where the word residual we get used a lot. This is not a difference between any observed variance or covariance at all. This is a residual variance, which means it's a variance of residuals. And the residual it's pointing to here is E, right, itself. So we didn't observe E, but let's think about what E happens to be, right? If we had, I'm going to get rid of my art here. You know what would be awesome? Is if I could see that somewhere downtown. Now I don't want you to like graffiti anything, but like sidewalk chalk or something like that. That would be cool. Or like little like, you know, like a message board or whatever. I was like, you could just litter pound WTF template or hashtag WTF template everywhere. Not litter, but you know, tape it everywhere. No. If we had Y here and we had Y hat. All right, let's imagine, I'm just picking some values of Y, 1, 2, and 3, and maybe we predicted this to be something like that, right? These are our predicted values. I don't even know what X is. E is the difference between Y hat and Y, right? So Y hat plus E has to equal Y. All right, so the difference between this is 2. The difference between this, here, I want to make this 4, is 2, and this is a negative 1. So what that variance is describing is it's like if we took E as our variable, if we had just observed E, that's its variance, right? Remember, we're comfortable with the topic of variance. We usually describe it as standard deviation. But what we're saying here is, hey, there's a lot of E, there's a lot of error to it, right? The variance of it, right? And so if we were to look at, if this was Y and this is X, and here's our regression line, and maybe this is our 3 points, you can see how close they are to the line. That has a certain amount of variation in this E right here. But perhaps, you know, if we compared it to a line that looked like this, right here, there's a lot more variation, right? Or better yet, if the dots were right on the line. How much variance is in that? 0, right? They're constants. So no residual variance means the line is perfectly fitting through all the points. Right? That rarely happens. Certainly never happens in social science. The things that deal with laws of physics, if we can measure them accurately, you get that. So E, what we're saying here with E is it's got a variance, and we don't know what that is. Now, instead of actually providing, doing this linear regression and counting up or tabulating the sums of squares error, which is how we estimated this previously, we're just going to define it as an estimable model parameter, which means it shows up in a likelihood function and it deals with that kind of grid search process or search and destroy, hide and seek Marco Polo process of maximum likelihood, where we plug in, I'm trying to think of positive terms, not search and destroy, where we plug in values for it and then try to figure out if it's at the peak, right? How we doing? That's E, okay? So we have one of those for Y. We also have an E for Z. What does that happen to be? What's its mean? 0. And its variance is sigma squared E for Z. Now that describes the same concept, but not for Y now. It describes it for Z. Right? If this is E of Y. We'd have to have another variable Z. We have a predicted value for Z, and then the difference would be the E for Z. So it's a different variable altogether. Right? Different term. But the same thing holds true. It's how much variation is there in what's left over after we do our prediction. Right? The thought being, if there's no variation left over, we've done our prediction really, really well. But if we've done if we do it very poorly, there'll be lots more variation. So that's E. But because we have 2 of those, what happens? we actually have to think about them a little bit differently. We're going to put this down here. They're actually going to be we're going to talk about their joint distribution, right? This is y all by itself. This is a marginal. These are marginal distributions. But really what we want to talk about is E jointly, and that's where that multivariate normal distribution shows up. Because we have two terms, this is like talking about a distribution. If I could draw it, here, I should draw it on here. If we could draw this multivariate normal distribution, boy, this is going to be tough. Me and a pen and a surface drawing a multivariate normal. All right? So here, maybe this is E for Y. This is E for Z. What the multivariate normal is doing is trying to give kind of their multiple dimensional likelihood. Right? So this is kind of a bell curve over them in multiple dimensions. So that's sort of roughly 3 dimensions there. I don't have that type of skill. I don't have that many skills, but when it comes to drawing, when it comes to handwriting, I've heard it from everyone in my life. Boy, your handwriting is terrible. Your handwriting is terrible. That's why I type usually. But I will say, if you think my handwriting is terrible, I've never had a letter sent back from me from the post office yet. Because it was illegible, okay? So it may be terrible, but it gets there. Sorry. Anyways, I digress. So with a multivariate normal, we know that we have a mean vector now, right? And that's the 0 mean vector. But we also know that we have, for each variable, we have the marginal residual variance for y. We have the marginal residual variance for z. But what is in this off diagonal now? The residual covariance, potentially. Oops, I don't know why I have sigma there. I do sigma y and z here. Sigma. All right. So that term, this thing, I'm going to put a question mark by. Because it's not guaranteed we need to estimate it. In fact, the residual covariance would be described like by looking at an arrow like this. Right? That is a residual covariance. That's what this thing represents. But in a path analysis, we talk, if you have a pair of boxes, right? You have a pair of variables here, y and z. There's only one, you can only have one type of connection between them, right? You can have the connection where you have the residual covariance, like that. Or you can have the connection where you have the direct effect, like that. But when you add a direct effect to an indirect effect, guess what happens? We end up getting one of those identification issues because we have what we would call a cycle, right? It is a recursive model, or excuse me, a non-recursive. I think we call this a non-recursive model, right? So if we follow the path from, if you want to get from y to z, you'd go down this arrow right here. If you want to get from z to y, you'd have to go, you can go all the way back. So you've got this kind of cycle going if you follow through with what's happening right here. So we can only pick one. And believe it or not, and this is one of the things that happened in your homework, and a couple of you pointed this out to me when you did this. Right? This setup, if we were to talk about the direct effect, this thing in Levon is represented with the tilde, right? The indirect effect is represented with the double tilde, right? Or the residual covariance. So if you had syntax where you said, oh, z tilde y and x, and y was tilde x, this is what the Levon syntax would be. But then you later on added the fact that you wanted the residual covariance between y and z. You put in y double tilde z like that. Right? This is an unidentified model. Right? If it ran, you would see things that would be out of line. You would see parameter estimates in the hundreds of thousands, or you'd see standard errors that were just off the chart, or maybe even negative. There's something numerically, you may be able to get the program to run with it, but the numbers it gives you are those ones that are unstable. Right? There's just no solution to it that's unique. So, one of the things I would tell you to do in this homework analysis is I'd say, well, you couldn't have both. You'd have to have one or the other, and so you may have taken that out, right? And you would have gotten your analysis to run, and hooray, you get a log likelihood, right? It's possible you may have chosen the other path. You may have said y tilde x, and then z tilde x, and then y double tilde. Oh, not double tilde like that. Double tilde z, right? You may have chosen that path, which would have been this model right here. And wouldn't you know, the log likelihood for this model right here, I call this model 0, and the log likelihood for 0 star, these two likelihoods, log likelihoods, are identical. They're equal. Isn't that terrible? So what does that mean? Right? Think of it in hypothesis testing. I was actually, and I think in the next hour I'll build some data. We simulate some data and I'll show this to you. Right? That means when you do this analysis, you run this model. Let's imagine you're trying to decide, do I have a direct effect between x or y and z, or do I have an indirect or a residual covariance between y and z? Right? So you run the model like this, and you get your log likelihood. And you run the model like that, and you get the log likelihood. Now these are not nested models, right? Because in one you're taking one away and adding something from the other. So you can say, well, I can use a AIC or a BIC to compare, and sure enough, the AIC and BIC are identical. They're equal fit. What it's telling you is that you cannot decide empirically whether the effect of y and z is undirected or directional. You cannot tell. They are equivalent models. How's that? You want one more? There's another equivalent model to this, right? This is like what I call model 0. This is what I call 0 star. What if I put the model in where I did the following? X predicts z, z predicts y. Or x predicts y, and then also x predicts y, right? So the Lavon syntax for that would be y tilde x and z, and then z tilde y. And wouldn't you believe it if I call this thing, I don't even know, log likelihood 0, I'll call it star, or I don't even know, just dot. This log likelihood is equal to both of the other two as well.
So we don't have x, z.
So what this is telling us is the direction between y and z is z predicts y. So in a path analysis, and this is what we stumbled upon in homework this week, when you were trying to figure out tildes versus double tildes and everything else, this is what you were doing. You were trying an arrow that would go one direction is a tilde from in this case, y where z is on it. An arrow that goes another direction is a tilde where z has y on it. And then a undirected path is where you have a y double tilde z, and it didn't show up on either of the tilde lines. But all three models are equivalent statistically. So, what that means, when a model is equivalent statistically, it's like saying any of these three are valid. You cannot differentiate between any of the three. So, how do you like that? So if someone comes to you and says the following, okay, y mediates the relationship between x and z, it's also true that that model fits equally well to the model where z mediates the relationship between x and y. And it fits equally well to the model where you'd say, yeah, x predicts y and z, and there's some residual correlation between y and z. Whoa. And you stumbled upon that when you were trying your homework. And some of you stumbled upon it correctly, right? I put in the output to the homework match your log likelihood. And thankfully, each of you is trying to do that. That's awesome. So you've got that part to it, and that's cool. I know how bad that must feel, though, because I know how long it takes sometimes to match these numbers, and it's frustrating. In Nebraska, when I taught there, I team taught with my wife, and she built a homework system online, and instead of trying to match a log likelihood, you'd have to enter something in a box, and it would turn green if you got it right. And the students there would complain about how it was red if it was wrong, and they'd be so angry at web browsers for having red boxes. And so this is just the same way. You've got WTF template, and you've got other things to yell at. I get it. But you could have gotten it right. And some of you did get it right. From this, which was not the model that we were trying to specify. So in a path analysis, and this is the neat thing about it, because you have all these things going along, not everything is differentiable. And really, if someone were to say, I don't know the relationship between Y and Z, I don't have a nice theoretical reason as to that, there would be, there would not be any good call as to why you'd have a path that looked like that versus a path otherwise. Anyway, questions on this? Yeah, Dan. The theory is supposed to be. Common sense and theory. If you have a variable that happens in a temporal order, right? So you collected like a grade. This is like your midterm grade, and this is your final grade, right? It's not possible temporally to say that your final causes your midterm grade. That arrow is the idea is hypothetically causes, right? The only way that your final could cause your midterm grade is for you to have a time machine, right? Or better yet, to randomly assign people to a time machine. Here's a true story for you. I had colleagues in political science at the university up north where I used to work who described a path analysis that essentially did this. They had political voting behavior from some earlier point in time, and it was predicted by what they had drawn, some type of chromosomal DNA analysis of people that they had in their study currently. And so they were predicting the past with current values. All right, so that's one obvious case, right? You can't go back in time. At least I can't. If any of you have a time machine, you can make millions. Billions, maybe. Have you seen Back to the Future? Part 2 with Biff, right? And hoverboards. So, now, theory. Theory is a throwaway to a lot of people in statistics. When we can't describe it, we just say theory. What I like to say is you cannot differentiate between the two. So even if you had theory, you couldn't decide between them. But in the case of obvious analyses, like you have the past, you typically have an order to it. For it. We're up against the break. So how about we take 10 minutes and come back and we'll keep talking about this, okay? Thanks. What was that?
Z to the X.
No. Z will never predict X. The only difference, X is always predicting both of these. The question is which.
X is predicting Z.
Oh yeah, pardon me. Thank you. Yes. Thank you. Sorry about that.
That's fine.
My apologies.
Next week, I'll be